In section 2.1, we're going to be looking at a new type of function called a piecewise function. And a piecewise function is one that comes in pieces. So before we get to that, let's do a quick little warm-up here. We're going to just do some sketching of some parent graphs, or kind of variety of parent graphs here. The first one says y equals 2 absolute value of x. So our absolute value of x, that's a parent function, has been multiplied by 2. So it's a vertical stretch. So the y-coordinate stays this, or the vertex stays the same. But instead of going over 1, up 1, we're going to go over 1, up 2, over 1, up 2, right? It's a v. A v is linear on both sides. So the slope on both sides is 2. All right, my next graph is an exponential. Exponential functions always go through the point 0, 1, because 2 to the 0 is 1. If I plug in a 1, 2 to the first is 2, 2 to the second is 4, 2 to the negative first is 1/2, then 1/4, then 1/8. Right? Exponential functions have that horizontal asymptote on the left. Sorry about all the shadows there. Horizontal asymptote on the left on the x-axis. My third graph is our square root, or our shooting star graph. Its domain is x is greater than or equal to 0, right? You can't take the square root of a negative. Goes through the point 1, 1, goes through the point 4, 2, and we'll go through the point 9, 3. It's just a couple little parent graphs in there that we may use later today. So a piecewise function, there we go. A piecewise function is defined as a function that uses different rules or different equations for different parts of its domain. So we'll say rules or equations for different values of x. For example, well, before we even get there, let's talk about the format. They'll say f of x equals, and then in this curly brace, they'll put more than one equation. We know this is a line, so it says y equals 2x minus 5, but then they'll tell us when they want us to use that. They only want us to use that when x is less than 3. So here's my, oh gosh, the axes didn't come out very well on this at all. Let me make these just a little bit darker here. So there's my x and y axis. And here's 1, 2, 3. Do you see how to the left of 3 we have the line? And then the second rule says we've got this graph, which is a parabola or a quadratic, to the right of 3. So if this is 3, we've got the parabola on the right side of 3. We have the line on the left side of 3. Now another thing to point out here is that this did not include the 3, so look, they used that open circle, whereas this domain does include the 3, so we want to make sure we fill that in. Okay, so all together, this graph with these two pieces creates this piecewise function. It's still a function. It still passes the vertical line test, as they always will if it's a true piecewise function. Okay, so we just want to make sure that in the end, if I were to, actually I have a vertical line here, I have a toothpick here I'm using for something else. But if I were to drag this toothpick along, it's only going to cross through the graph once. Okay? All right. So let's talk about how we graph these. All right, so here's a piecewise function for us. I'm going to switch to a pencil, and I think you might find that to be helpful as well, something that you can erase. So we've got f of x equals 2x plus 3 when x is less than negative 2, and 1 minus x when x is greater than or equal to negative 2. So I have the line y equals 2x plus 3. Well, the y-intercept is 3, and the slope is a positive 2. I'm going to go ahead and just draw the whole thing with a pencil. So very lightly with my pencil, I'm going to go graph the line y equals 2x minus 3. But they only want that graph when x is less than negative 2. So here's negative 2. I only want this part to the left of negative 2. And it does not include the negative 2, so we'll make that open circle there. Okay, you can take your pencil now and erase the portion of that line that we didn't use. Okay, good. Let's talk about that second piece. That second piece, if we read that, is y equals 1 minus x, or if you prefer, negative x plus 1, which is a line that starts at 1. I'm using my pencil again, and it has a slope of negative 1. And so I can go in with my pencil and just very lightly draw in that entire line. But remember, they only want it to the right of negative 2. So again, here's my negative 2. So I'm going to go up and find where that starts, fill it in because it says or equal to. I'll try to hit some better points there this time. And so I only want the line to the right of negative 2. So now when I go in, my vertical line test, my toothpick, right, nothing, a lot of shadows there, but notice it's only passing through at one point. Okay, good. So how could we check this on a graphing calculator? Well, there's a couple of different, obviously it depends on which calculator you have. I should have had mine turned on. I'm going to start with an Inspire, and I'm going to add a graph page. Okay. Now, when I hit my templates button is just to the right of the 9. It pulls up all of these templates. And when you look, this one up here has that curly brace on the left, and you can't really see it here, but it's got some boxes and some commas. So I went to a graph page. Let's change this exposure a little bit here so you can see that a little bit better. Good. I went to a graph page. Here's my f1 of x, and then I inserted this template. So I have 2x plus 3. I'm just typing it in. The comma's already there. And now I go to the restriction. X is less than. My less than on this calculator is where my equal sign is. So I'm going to hit Control equals. And that pulls up my less than. And I've got my negative 2. I'll go down and I have 1 minus x. And this is when x is, Control equals, greater than or equal to negative 2. And then I just hit enter. Now it's not going to use different colors, and I kind of like that about it. It's not going to use different colors because it's a good reminder that this is just one function. Okay, but now we can kind of see that relationship with what we have. Okay, notice this calculator will not show you open circles versus closed circles. No calculator will, because remember, an open circle is just the absence of a point, and a filled in circle is just a point, but a point is super tiny anyway. So a calculator will never really exaggerate that as we do. Okay, we'll check the next one on a different calculator. Okay, all right, let's take a look at this one. We have h of x equals x squared plus 3 when x is less than 0. H of x equals the square root of x plus 3 when x is greater than or equal to 0. So again, this graph is going to split at x equals 0. And by the way, I kind of, since I wrote on top of it, right above here, I really missed this big point here. It's kind of a big deal. Note, we will refer to the x value where the function changes as the transition point. So I started to use that phrase down here, and then I realized we hadn't talked about it. This graph transitions from a parabola to a shooting star when x equals 0. So this is my transition point. Okay. All right, so let's go draw this. I've got a parabola that's been moved up 3. So the vertex is up here at 3, over 1, up 1, over 2, up 4. Symmetry gets us to the other side. We can draw the whole thing. Just a tiny little parabola there. But now I'm going to go in, and I only want this graph when x is less than 0. So here's 0. I only want the graph on the left side. And it did not include 0, so I'm going to try to exaggerate that with that open circle. And then I'll just go in and very lightly erase the piece that I don't want. Okay. My next one is y equals the square root of x plus 3. Well, we already drew the square root of x today. That was one of our warm-up questions. I'm just going to move it up 3. So it's a shooting star graph that's been moved up 3. So from there, 1, 2, 3, 4, and up 2. Okay. And this graph starts at 0 and goes on forever. Good thing. We only want to use it when x is greater than or equal to 0. By the way, let's talk about that or equal to. We have a point here. There wasn't a point, but now there is, right? So we fill in that circle, because again, an open circle means there's no point there. Well, I just put a point there. And we're actually going to use this entire square root graph. Let's grab a calculator, an 84 this time, and let's talk about typing this in. So I grabbed an 84. It may look a little bit different than your 84, but if I would like to do, a piecewise function here, we're actually going to have to do it in 2 different functions. So I'm going to type in my x squared plus 3, and this is going to seem very silly, but this is how the calculator is programmed. I'm going to divide by, parentheses, x is less than 0. My less than is in my test menu, which is above the math button. So I'm going to hit second math, and there they are. So x is less than 0. So I type in the function divide by the restriction. I go down here, I type in the square root of x, get out of the square root, plus 3, and divide that by, parentheses, x, and then second math, greater than or equal to 0. Excuse me. Now we're probably going to want to change our window, but we kind of see that little change our, coincidentally, well, it's the opposite colors, but let's go change this window. I'm going to hit zoom 6. Zoom 6 is going to give us that negative 10 to 10, negative 10 to 10 window. Good. So it's half of a parabola and then the entire square root function. Okay? All right. Let's take a look at these questions here at the bottom. It says find the following function values. H of negative 3, h of 0, h of 16. Remember, this is h of x. This is our equation. And we've done this before, right? Function notation says go to the function called h and plug in a negative 3 for x. Well, the question is, which one do we plug into? Well, let's look at our graph. At negative 3, we'd be on the red graph, wouldn't we? Why? Because negative 3 fits into this domain. This is the rule for these x values. So we're going to plug it into the x squared plus 3 to get a value of 12. Okay. Let's take a look at the second one. H of 0. Well, by the way, we can see that in our graph. But h of 0, which of these domains include 0? This one, because it says or equal to. 0. So we're going to plug this one into the second equation. And I get 3, which that doesn't surprise us because we see it on the graph. H of 16. 16 is greater than 0. So we're going to plug it into that second rule. And I get 7. So if we want to find a y value, we need to know which equation are we using. Let's take a look at this one. So again, we've got pieces. This time we've got 3 pieces. So the first one says y equals 2 minus x, which we did something like that already. If you would like, call it negative x plus 2. So I have a y-intercept of 2 and a slope of negative 1. Just very lightly with my pencil, I'm just going to draw that whole line in there. Remember, we've got that line, but we only want it to the left of negative 1. Here's negative 1, and by the way, or equal to, so I'm going to go find where I am on that line at negative 1, fill that in, and I'm only using the side to the left because it says x is less than negative 1, so that's to the left of negative 1. And I'm going to get rid of the rest. Let's look at the second piece. Remember, k of x means y, right? So the second piece says y equals 3. Well, that's just a horizontal line, isn't it? So I'm going to go graph the line y equals 3. 1, 2, 3. There's the line y equals 3. But they only want that when x is greater than negative 1, but less than or equal to 3. So they're essentially telling us that we only want to use that graph. Sorry, I'm going to label my transition points. We're only going to use that graph between negative 1 and 3. Now, we're not including the negative 1, but that's okay. There's already a point there. But we are going to include the 3. I'm going to go in then and erase everything else. I know my graph looks a little cluttered because I can see the graph that we did on the other side of our notes. It's okay. All right, last piece says y equals negative 2. Also a horizontal line. This horizontal line is when x is greater than 3 but less than 7. And so here's 7 out here. So we're going to use that graph from 3 to 7. We don't include the 3. We don't include, I went a little past 7. We don't include the 7. And I'm going to get rid of the rest of that graph. So this is a piecewise function. It had 3 pieces. 2 of them happened to connect. The third one didn't, and that is okay. All right. Can we check that on our calculator? Sure. We know with the 84, we would just then keep typing in something else. On the Inspire, if I would like to graph 3 pieces, I'm going to go back to that templates button, which is to the right of the 9. I'm just going to go to the next one. This time it says, well, how many pieces do you have? See how we can adjust that? Sorry. How we can adjust that 4, 5, 6, 7. Well, we certainly don't want that many pieces. We just have the 3. And I'm not going to take the time to do it, but now whoops, you can't even see that. Now it gives us that template for us to type in more than 1. Okay. All right, so we can absolutely do that on both calculators. Okay. I'd like you to pause the video at this point, and I would like you to write in the piecewise function shown below. Before you pause, I should say I'm going to go ahead and get us all started. We have seemingly, well, you could look at this 3 different ways. You could look at it as 2 lines to create the V and a horizontal line. Or you could look at it as an absolute value graph and a horizontal line. So you need to make the determination if you're using 2 graphs or 3. I'm going to use 2. So I'm going to get myself a template. Right? We only write y equals once, and then we put our curly brace. You'll have your function equations, and then you'll have your restrictions. So you can go ahead and pause, see what you can come up with, and we'll go from there. Okay, so I saw this as the absolute value graph. Pretty much very similar to our warm-up question, right? Look at the slope on either side is 2 or -2. Looks like it's been moved to the right one. So I have the 2 out in front, and then I have my absolute value of x minus 1. I only want to use that graph until I get to x equals 3. So x is less than or equal to, right? See that filled in? 3. Good. And then our second piece is the horizontal line, y equals -1. I'm going to start that at 3. It goes on forever. There was an arrow at the end that kind of covered up. Notice again, I did not say or equal to because it's not filled in there on that horizontal line. Okay. All right. So what you've seen with some of our piecewise functions that we've done today is like back here we said some of the pieces connect, some of them do not, right? These 2 pieces did not connect. Well, as we start looking at graphs that don't connect, we start talking about this idea of continuity. So it says we will formally define continuity later in the course. For now, we can say a function is continuous if you can draw the graph without lifting your pencil from the paper. So it says here are graphs of 2 continuous functions. So notice I can draw this entire thing without lifting my pencil off the paper. Same thing goes here. I mean, there's something funky going on here, but I can draw this entire thing without picking up my pencil. That cannot be said about this last graph here, right? I have coming down here and I turn and go up, pick up my pencil to get down to the second piece. Okay. They're asking us to graph one more piecewise function. And then it says, is the function continuous? And then we'll state the domain and the range. All right, so let's take a look at this first piece. We have y equals 2 to the x. Oh, we did that in our warm-up also. So we already talked about what this graph will look like. In fact, if we plug in a 3, we go all the way up to 8. Right, it has that horizontal asymptote on the left. And they want this graph when x is less than 2. So here's 2, open circle there, and I want everything to the left. And I'm going to go take my pencil and erase what I don't want. Okay. My second piece is y equals 8 minus 2x, or negative 2x plus 8. So we're starting up here at 8. We're going down 2 over 1, down 2 over 1, down 2 over 1, down 2 over 1. So I start to get that nice little line drawn in there. They want me to use this graph when x is greater than 2, not including 2. So I don't include that still. And then we've got this piece right here. All right, so the question is this graph continuous? Can I draw, now that I have it, can I draw this entire thing without picking up my pencil? And the answer should be no. We have a problem up here. Point missing. So if there's a point missing, I need to pick up my pen so I can jump to the other side of that hole and continue drawing. So we're going to say it is discontinuous at x equals 2. Okay. All right, let's state the domain and range, and let's make sure we're using interval notation. Remember, domain is x and range is y. So which x's do I use? Well, it looks like I use all of them except for 2. So from negative infinity to 2, and then again from 2 to infinity. And then let's talk about the range. This graph is going to go down forever, but this graph is not going up forever, right? The highest this graph ever gets is this, well, almost to this point. So in terms of the y's, we're going down forever. So negative infinity is my lowest, and the highest point we'll get to is 2, but not including. Oh, that's not a 2, that's a 4. I'm sorry. The highest y value we almost get to is 4.